Welcome back to the channel, everybody. This is a new series that I'll be putting out hopefully once a week. And I think it's important as a geologist to stay up to date on the new technology, the new research that's going on in the world. You know, just in case you're a student that is just graduating from, undergrad college and you want to look into a master's and you don't know what you want to do yet. Hopefully this series will help you kind of formulate some ideas. And also, it's important to stay up on geologic news in general. So we'll be running through, this is going to be more than the last week, but at least the last month of geologic news. And every week I hope to post an episode just covering, the recent news related to geology. And I'm using 3 different websites, and you'll see them as we go through these articles. So let's just jump right into our first article. So this is from Geology page, going with the grains to explain a fundamental tectonic force. A new study suggests that tiny mineral grains, squeezed and mixed over millions of years, set in motion the chain events that plunge massive tectonic plates deep into the Earth's interior, or subduction. The theory proposed by Yale scientist David Berkovici, I'm going to butcher so many names, and Elvira Molyakova may provide an origin story for subduction, one of the most fundamental forces responsible for the dynamic nature of the planet. The study appears in the Proceedings of the National Academy of Sciences. Subduction occurs when one tectonic plate slides underneath another plate and then sinks into the Earth's mantle. That's based on, if you guys don't remember, density differences. The lower density plate will go above the subducting plate. The heavier, denser plate will subduct underneath the lighter, denser plate. Its role in major geological science processes is immense. It is the main engine for tectonic motion. It builds mountains, triggers earthquakes, forms volcanoes, and drives the geologic carbon cycle. Yet researchers have been uncertain about what initiates subduction. According to the theoretical model developed by Berkovici and Molyakova, a research scientist at Yale, subduction may initiate at the margins between Earth's seafloor and continents. The model shows that tectonic stresses in an oceanic plate causes its mineral grains to mix with each other, becoming damaged and eventually shrink over a period of approximately 100 million years. This process weakens the oceanic plate and makes it susceptible to vertical shearing and bending, which are associated with the start of subduction. The real bottleneck for tectonic plate activity on a terrestrial planet is how fast its massive rocky layers can deform. The rocks can deform only as fast as their tiny mineral grains allow. Our model explains how these changes in mineral grains can dramatically weaken the rock and make subduction possible on a planet like Earth. So this is basically just going more in depth. What we're taught in school is subduction is due to density differences. This is going even deeper and explaining the mineral grains in each rock and how the damage that occurs at the subduction boundary, the mixing and the damaging of the grains in each rock is the reason that subduction occurs initially. That's pretty interesting. You'll have your initial fractures occur, and this will go to the Wilson cycle where a subduction zone will initially occur. You start out with a rift zone, and then eventually it becomes a subduction zone where the rift zone will die and it'll become a Wilson cycle, start subducting again, and the plates will come back together. This is a pretty interesting read. So we have a newly discovered fossil, and it's likely a subaqueous insect, kind of like the sea scorpions, I'm guessing. So, and it's a trace fossil. A newly discovered trace fossil of an ancient burrow has been named after University of Alberta paleontologist Murray Gingras. The fossil discovered by a former graduate student has an important role to play in gauging how salty ancient water bodies were, putting together a clear picture of our planet's past. Trace fossils are a type of fossil that preserves activity of ancient life in the geological record. They include fossilized footprints, nests, droppings, and in this case, a fossilized burrow dug by an organism that lived in a watery environment. Those are called scolithos, the burrows. The fossilized burrow, named Glossofungitis gingrossi is from the late Cretaceous of central Utah and was home to water-dwelling insects similar to mayflies more than 90 million years ago. Wow. Fossils like this are significant because they help us narrow down what type of organism dug the burrow, which in turn will tell us about the salinity of the water in which they lived. So this insect, this basically a mayfly, is going to allow people to use this trace fossil, index fossil, to determine the environment at which in this case, probably a sedimentary rock was deposited. These mayfly like creatures created burrows, and they must be very distinct. There's no pictures of these burrows in this article, but sounds interesting for anyone that's interested in geochronology. So the next one we're looking into is deep slow slip action may direct largest earthquakes and their tsunamis. So a megathrust earthquake and subsequent tsunami that originates in subduction zones like Cascadia, Vancouver Island, Canada to Northern California are some of the most severe natural disasters in the world. Now a team of geoscientists thinks the key to understanding some of the destructive events may lie in the deep, gradual, slow slip behaviors beneath the subduction zone. This information might help in planning for future earthquakes in the area. What we found was pretty unexpected. Unlike the bigger, shallower megathrust earthquakes that move and put out energy in the same direction as the plates move, the slow slip earthquakes' energy may move in other directions, primarily down. Subduction zones occur when two of the Earth's plates meet and one moves beneath the other. This typically creates a fault line and some distance away, a line of volcanoes. Cascadia is typically in that tectonic plates. Oh my goodness. Cascadia is typical in that the tectonic plates meet near the Pacific coast and the Cascade Mountains, a volcanic range containing Mount St. Helens, Mount Hood, Mount Rainier, forms to the east. According to the researchers, a megathrust earthquake of magnitude 9 occurred in Cascadia in 1700, and there has not been a large earthquake here since then. Rather, slow slip earthquakes, events that happen deeper and move very short distances at a very slow rate, happen continuously. You know, a big slip will release a lot of energy that is built up in that fault boundary. And when it's slow slipping, that means that a lot of energy is being released continuously instead of just one big one. So that's kind of explaining what's happening here. Slow slip earthquakes occur at a deeper depth than the earthquakes that cause major damage and earth-shaking events, and the researchers have analyzed how this deep slip may affect the timing and behavior of the larger, damaging megathrust earthquakes. According to the researchers in southern Cascadia, the overall plate motion is about an inch of movement per year, and in the north by Vancouver Island, it is about 1.5 inches. That's a lot of movement. You accumulate that over, thousands or millions of years, that's a lot of movement. Slow slip events in Cascadia occur every 1 to 2 years, but geologists wonder if one of them will be the one that triggered the next megathrust earthquake. Researchers measure surface movement using permanent high-resolution GPS stations on the surface. The result is a stair-step pattern of loading and slipping during slow slip movements. The events are visible on the surface, even though geologists know they are about 22 miles beneath the surface. They report their results in geochemistry, geosystems. So for anyone that's interested in structural geology / plate tectonics, that's your bread and butter right there. So that's interesting, and it makes sense that slow slip would kind of take away the possibility of these larger earthquakes. A large earthquake hasn't occurred in Cascadia since 1700. That's pretty interesting, and that's probably due to the fact that there's these deep slow slip movements, which is releasing energy and not allowing these bigger ones to build up. And then once those release, that's going to be a huge tsunami, huge destruction. So here's another earthquake one. This one's from USGS, and it's called "The Disaster That Helped the Nation Prepare for Future Earthquakes, Remembering San Fernando." This earthquake struck Southern California 50 years ago, killing 64 people and costing over $500 million in damage. The quake prompted federal, state, and local action to reduce earthquake risks and bolster public safety. At 6 o'clock in the morning on February 9th, 1971, the reservoir keeper of the Lower Van Norman Dam in Southern California tried to get out of bed. He couldn't. A magnitude 6.6 earthquake was shaking his home nestled at the bottom of the dam. After checking on his wife and child, he drove to the top of the dam to examine the damage. It was hard to believe what I saw. The Lower Van Norman Dam, which sat above the San Fernando Valley in Los Angeles County, had nearly collapsed in the wake of the quake. As wind-whipped waves chewed at the damaged lip of the 1,100-foot Van Norman Dam, police spread through a 9-square-mile area between the reservoir and the Ventura Freeway, warning residents to evacuate. The Los Angeles Times reported on February 10th, 1971. Approximately 80,000 people did evacuate as officials lowered the water levels in the dam. The 1971 San Fernando or Silmar earthquake was the worst to hit an urban area of California since the 1933 magnitude 6.4 Long Beach quake. It led to 64 deaths and more than $500 million in damage. It prompted Governor Ronald Reagan to declare Los Angeles County a disaster area, and the President Richard Nixon to send Vice President Spiro Agnew to inspect the area. NEHRP agencies, including the federal FEMA, the National Institute of Standards and Technology, the National Science Foundation, and the USGS, made research and policy recommendations that in part contributed to the city of Los Angeles enacting an ordinance in 2015 to retrofit weaker first-story wood frame buildings and non-ductile or brittle concrete buildings, which are both more vulnerable to collapse during strong shaking. In 2013, San Francisco enacted the mandatory soft story retrofit program, which was based in part on work sponsored by NEHRP on the aftermath of the 1989 Loma Prieta earthquake. It's another one about earthquakes and how humans are going to modernize themselves to just be able to handle and mitigate the risks behind these earthquakes. All right, so this is the ultimate reason why I got interested in geology, and it's not what I do for a living now or anything, because studying Yellowstone would be a very niche thing. You probably need a PhD. But the Yellowstone hotspot. The Yellowstone hotspot, the source of heat that powers Yellowstone's vast volcanic system, has been thought to have initiated about 17 million years ago. A growing volume of evidence, however, suggests that it has been around much longer. Yellowstone sits above a melting anomaly within the Earth called a hotspot. This hotspot is powered by a plume of hot but not molten material that may extend as deep as the boundary between the plant's mantle and core. As hot material rises buoyantly, it decompresses and melts near the surface, generating magma that feeds the magma chambers beneath Yellowstone and provides the heat that powers the many geysers and hot springs. A hotspot is stationary relative to the moving tectonic plates that make up Earth's surface. As the North American plate moves to the southwest over the hotspot, the center of volcanic activity therefore appears to be migrating to the northeast. There is thus a trail of volcanism that stretches to the southwest from present-day Yellowstone across the Snake River Plain of southern Idaho, getting progressively older along the trend. These older volcanic centers are essentially ancient Yellowstones, and some were responsible for especially powerful eruptions. The start of the trail is a 17-million-year-old McDermott volcanic system and similar age volcanism in northern Nevada and southern Oregon. Yellowstone-style volcanic eruptions weren't the only thing happening 17 million years ago. That time period also saw the eruption of the Columbia River Basalt, a tremendous outpouring of lava from vents in eastern Oregon and Washington and western Idaho. The lava from these vents flowed all the way to the Pacific Ocean and is responsible for some of the impressive features along the Oregon coast, like Haystack Rock and Cape Lookout. For many years, it was assumed that the Columbia River Basalt eruptions represented the start of the Yellowstone hotspot. The first eruption of a hotspot would likely be voluminous, and since the head of a mantle plume would be charged with heat and induce tremendous melting, and there were no obvious signs of older volcanic systems to the southwest of the McDermott age volcanic centers, the trail essentially went cold. A growing body of evidence, however, suggests that the Yellowstone hotspot was active before that time and is far older than previously thought. In fact, it was probably initiated well off the coast of North America. That's cool. It's preserved in the coastal mountains of Oregon and Washington is the evidence of massive volcanic eruptions that occurred offshore about 55 million years ago. Some of the lava from these eruptions was scraped up and welded onto the North American coastline by subduction, and still more exist on the ocean floor offshore of the Pacific Northwest. This so-called Silesia terrain has chemical and physical characteristics that suggest it formed due to a mantle plume, and it has a composition similar to the Columbia River basalts, indicating that the two large lava flow provinces are related. Might the Silesia terrain have formed due to an early version of the Yellowstone hotspot? If this is true, then the North American continent would have begun to override the hotspot about 40 million years ago. Sure enough, there are volcanic rocks of this age present in the Oregon and Washington Coast Range that are chemically related to the older Silesia rocks and younger Yellowstone hotspot products. Silesia and related rocks of the hotspot were originally welded onto the North American continent in coastal California and Oregon. But since that time, tectonic forces have caused northward migration of these rocks by as much as 300 kilometers to their current position in coastal Oregon and Washington. Wow, crazy. Volcanism, presumed to be driven by heat from the Yellowstone plume, continued east of the Cascade Mountains in southern Oregon and northern Nevada during 20-30 million years ago as the North American plate continued to move over this ancient Yellowstone hotspot. But these eruptions declined dramatically about 22 million years ago and stopped altogether 20 million years ago, beginning a hiatus of several million years. This pause ended with the eruption of the Columbia River basalt. So what happened? What stopped the eruptions? The most likely culprit is a slab of previously subducted oceanic crust, which was uplifted by the buoyant plume and trapped beneath the North American continent. This barrier effectively blocked the flow of material from the Yellowstone hotspot to the surface. Magma was still generated, but it was backing up behind the barrier. The accumulated magma finally punched through 17 million years ago, breaking the ancient slab and resulting in the Columbia River basalt eruptions. Then began the progression of volcanic calderas to present-day Yellowstone. About 20 years ago, the story might have been dismissed as fantasy. Through years of careful accumulation of data and evidence, however, the case has been quite strong. The Yellowstone hotspot is a long-lived feature that dates back at least 50 million years ago and perhaps even earlier. This evolution in thought is a good example of how continued data collection and study are critical and can shift our view of geologic history, even changing our understanding of something as important as the Yellowstone magmatic system. So like I said, this is the main reason I initially wanted to get into geology. I remember doing a research report on Yellowstone. It's fascinating stuff. And it's pretty cool that it's connected to those river basalts that you see on Google Earth. If you pull up Oregon and Idaho, that area, you'll just see this big black spot that's pretty obvious from Google Earth. And I'll probably include that in the video once I edit this. But it's kind of went through a differentiation, and as it's progressed from that, initiating the Columbian River basalts, and obviously plate tectonics has moved the plate over. The hotspot hasn't moved. It's the plates that have moved, and the Yellowstone is now in Idaho, Wyoming, Montana. It's spread across a pretty large area now. And they've been saying for years that it's due for a major earthquake. The last one happened, 700,000 years ago, I believe. And it occurs on that interval. So, that's why they study it so much, because it's supposedly due for one. If that thing were to go off, whew, damage, it would probably kill the American economy.